In this lecture, we are going to talk about how to construct shear and moment diagrams. Shear and moment diagrams are the topics that were already discussed in statics, but they are needed also in mechanics of materials in order to identify the magnitude of shear and moments at different parts of the beam. The goal of making shear and moment diagrams is to identify the value of the maximum shear and moment at any point in a beam. Let's start with understanding what are shear and moments in a beam. Consider a beam that is not subjected to any load. That beam doesn't have any internal force. But if a beam is subjected to any external loading, there should be some sort of internal forces in order to maintain equilibrium in the beam. Those are known as internal forces. And basically there are three different types of forces: axial force, shear force, and bending moment. Axial force is already discussed in the axially loaded elements. In beams, we are typically interested in shear force and bending moment. And in this lecture, we want to learn how to construct shear and moment diagrams in a beam. Different methods could be used for constructing shear and moment diagrams. Here we are going to talk about graphical method, which is relatively simple method for constructing shear and moment diagrams. The first step in drawing the shear and moment diagrams for a beam is to determine the reaction forces in the structure. And this is done by using the free body diagram. The free body is created by removing all restraints and replacing them with reaction forces. Basically, there are three different types of supports in a beam: the pen support, the ruler support, and the fixed support. Let's look into them one by one. The pen support restrains the movement of the beam in a vertical and horizontal direction, but allows for free rotation of a beam. Ruler support restrains the movement of a beam perpendicular to the direction of the support, but allows for the free movement of the beam in the axial direction, and also allows for the free rotation. And the last one is the fixed support that restrains the movement of the beam in the horizontal and vertical direction, also restrains the rotation of the beam. Note that the graphical presentation of the supports that are shown in these figures are not representing how these supports are made in the real-world structures. For instance, a pen support is typically made by connecting the middle part of the beam, known as web, to the support that allows for the transferring the axial force and shear force. But because the top and bottom part of the beam are not connected, the moment cannot be transferred effectively and can be ignored. The ruler support is somehow similar to the pen support. The difference is on the shape of the hole in the connecting plate that allows for a slight movement of the beam in the axial direction. In this connection, the axial force is not transferred, but the shear force could be transferred by the connection. In the fixed support, all parts of the beam are connected to the support, including the middle part of the beam, known as web, and the top and the bottom part of the beam, known as flange. In this connection, shear force, axial force, and bending moment could be transferred from the beam to the support. After releasing all the supports and replacing them with the reaction forces, the free body diagram is made. In order to determine the magnitude of reaction forces, we need to use equilibrium equations. In two-dimensional problems, there are three equilibrium equations. Some of the forces in the x direction should be equal to 0. Some of the forces in the y direction should be equal to 0. Also, some of the moments should be equal to 0. So there are three equilibrium equations, and as long as the number of reaction forces are 3, they could be determined just by using equilibrium equations. These structures are known as determinate structures. On the other side, if there are more than 3 reaction forces, then the equilibrium equations are not sufficient for determining those reaction forces, and these structures are known as indeterminate structures. In this lecture, we just focus on determinate structures, but in future, we will also cover structures that are indeterminate, and we will talk about how to determine the reaction forces in those structures. The next step is to draw the shear diagram. The shear diagram always starts from the left end of the structure. There are 3 rules that govern how to draw the shear diagrams. The first rule talks about the beginning point of the diagram. At the beginning part of the beam, on the very left end, the magnitude of the initial shear force is equal to the amount of concentrated force acting at that point, whether that concentrated force is an external force or it is a reaction force. If the force is upward, the initial value is going to be considered positive, and if the force is downward, the initial value would be negative. If there is no concentrated force and there is no support at the very left end, the initial value of the shear diagram is 0. Note that the distributed load is not causing an initial value of shear in the shear diagram. Rule number 2 says the change in the shear diagram from one point to another point is equal to the area under the loading between these 2 points. If there is no loading, shear diagram remains constant between these points. For instance, look at this beam. At the left side, there is an initial value of shear force equal to Ay because of the reaction force. The shear force remains constant all the way to the middle of the beam before reaching to that concentrated force of P, because there is no loading from the left support all the way to the middle part of the beam. Another example is a simply supported beam that is subjected to a distributed load of W. The initial value of the shear force on the left side is equal to the amount of the reaction force, A sub y, but the shear force does not remain constant because of the distributed load. The distributed load is downward, so the shear force is linearly decreasing when we move from the left side to the right side of the beam. The slope of the shear diagram is equal to the magnitude of the distributed load W. The rule of thumb for constructing the shear diagram is that the shear diagram is always 1 degree higher than the loading. Like in the first case, there was no loading from the left support all the way to the middle part, and the shear diagram remained constant. In the second example, the distributed load is constant along the length of the beam, and the shear diagram is varying linearly. If the loading is linear, then the expected variation in the shear diagram would be a second-order polynomial, and so on. Rule number 3 says an external concentrated force causes a jump in the shear diagram. If the force is downward, the jump will be downward. If the force is upward, the jump will be upward in the shear diagram. After making the shear diagram, it's time to make the moment diagram. Similar to the shear diagram, there are some rules that could be used for constructing the moment diagram. Rule number 1 says the initial moment at the very left end of the beam is equal to the external moment acting at that point, or it's equal to the reaction moment if there is a fixed support at the left end. The initial moment value is 0 if the structure is not restrained by a fixed support and there is no external moment at that point. Rule number 2 says the change in the moment from one point to another point is equal to the area under the shear diagram between these 2 points. In other words, if shear is 0, the moment remains constant. If the shear is constant, the moment varies linearly. If the shear is linear, then the moment varies as a second-order polynomial, and so on. So the order of the moment diagram is always 1 degree higher than the order of the shear diagram. Rule number 3 deals with the external concentrated moments acting on a beam. An external concentrated moment causes a jump in the moment diagram. A clockwise moment causes an upward jump in the moment diagram. A counterclockwise moment causes a downward jump in the moment diagram. These rules could be used for determining the shear and moment diagrams for any beams. Let's look into an example together. Beam ABC is supported by a pin support at the left end at A and a roller support at B, and it is subjected to a distributed load of W from B to C. We want to draw the shear and moment diagrams for this beam. The first step is determining the reaction forces. The pin support at the left is replaced with 2 reaction forces, AX and AY, in the horizontal and vertical direction. The roller support at B is replaced with a reaction force of B sub y at B. Some of the moments around point B should be equal to 0. AX and BY are not producing any moment around that point because they are passing through point B. AY is producing a clockwise moment, and the magnitude of that would be equal to AY multiplied by its distance to point B, which is shown by L. On the other side, the moment caused by the distributed load is equal to W multiplied by the length at which it is acting on, A, multiplied by A over 2. And it is also clockwise. So sum of these 2 moments should be equal to 0. Solving that for AY shows that AY is going to be equal to negative WA squared divided by 2L. Negative here means that force AY should be downward. Then we use sum of the forces in the y direction equal to 0 in order to determine the other reaction force. A sub y plus B sub y should be equal to the resultant force of the distributed load, which is W multiplied by A. So from that, solving for BY, By is going to be equal to WA multiplied by 1 plus A divided by 2L. The next step after determining the reaction forces would be drawing the shear diagram. Starting from the left side, rule number 1 says the initial value of the shear diagram is equal to the reaction force at that point. Because the reaction force is downward, the shear force is going to be negative. Shear force remains constant while moving from A to B, because there is no load acting from A to B. At B, we use rule number 3, which says there is a jump in the shear diagram when there is a concentrated force. So at that point, the shear diagram jumps up with the magnitude of reaction force at B. After that, the shear diagram is decreasing by a slope of W because of the distributed load. And it goes back to 0, showing that the shear force at the very right end is equal to 0, which validates the solution, because at the very right end, there is no concentrated force and there is no support. After constructing the shear diagram, it's time to draw the moment diagram. Starting from the left side, there is no concentrated moment and there is no fixed support. So the initial moment at the left side is going to be equal to 0. Moving to the right side, the shear diagram is constant with negative value, which means the moment diagram linearly decreases. The magnitude of the moment diagram right before getting to the support at B would be equal to the initial moment, which is 0, plus the area under the shear diagram, which is shown by A1. Area 1 is equal to the reaction force multiplied by length L. So that would be equal to WA squared divided by 2 with a negative sign. When moving from left of B to the right of B, there is no jump because there is no concentrated moment. After point B, the moment diagram goes up because the area under the shear diagram. The magnitude of the moment diagram at the very right end is equal to the initial moment at point B plus area 2, which is the area of the triangle of the shear diagram on the right side. The area of that triangle is 1/2 of its base multiplied by its height, which is WA squared over 2. And that gives 0 moment at the very right end of this beam, which shows the calculation is correct, because at the very right end, there is no fixed support and there is no concentrated moment. This was a basic example to demonstrate how to use graphical methods to construct shear and moment diagrams. Alright, now let's look into another example with more complex loadings in order to make sure the concept is understood properly. The beam shown in this figure is supported by a pin support on the left side at A and a ruler support at B. The beam is subjected to a concentrated moment of 4,500 pound-feet at A and a distributed load of 700 pound/feet, and also a concentrated force of 1,300 pound is acting at the very right end of this beam. And you want to construct the shear and moment diagrams. Similar to the previous problem, we start with replacing the left support with 2 reaction forces, AX and AY, and supported B with 1 reaction force, which is, we call it B sub Y. Sum of the moments around A should be equal to 0. Assuming clockwise is positive, the concentrated moment at A is getting negative sign, so that would be negative 4,500 pound-feet. The moment produced by the distributed load is equal to the distributed load multiplied by the length at which it is acting on, so that would be 700 multiplied by 8, multiplied by the distance of the resultant force to support at A, which is 5 feet plus half of 8. This moment is clockwise, so it is getting a positive sign. The next force is the reaction force at B. The moment produced by that is equal to the magnitude of that force multiplied by its distance to A, which is 5 feet plus 8 feet plus 2 feet. The last moment is the moment produced by the concentrated force at the very right end, and that is equal to the magnitude of the force, 1,300 pound, multiplied by its distance to A. This moment gets positive sign because it is clockwise. Some of these moments should be equal to 0, from which we can determine the amount of reaction force at B, which is 4,790 pound. Then we use sum of the forces in the y direction equal to 0, which means AY plus BY is equal to the distributed load multiplied by the length at which it is acting on, plus the amount of concentrated force, 1,300 pound. From that, the reaction force at A would be equal to 2,110 pound. After determining the reaction force, it's time to make the shear diagram. Starting from the left side, there is a reaction force with a magnitude of 2,110 pound. In the opposite direction, that means that the initial value of the shear diagram at the left end is 2,110 pound positive. Moving from that point, all the way before getting to the distributed load, the shear diagram remains constant because there is no loading in between. After reaching to the distributed load, the shear diagram decreases with a constant slope of W. The magnitude of shear at the end of the distributed load is equal to the initial value, 2110 pounds, minus the area under the loading, which is 700 multiplied by 8, which results in negative 3490 pounds. The shear diagram remains constant all the way to support B. At that point, there will be a jump upward with the magnitude of the reaction force at B. The reaction force at B is 4790 pounds, so the shear force right after support B would be equal to 1300 pounds. Note that the shear diagram is discontinuous before and after the support because of the jump caused by the reaction force at that support. After point B, the shear diagram remains constant because there is no loading, and at the very right end, it goes back to 0, which shows the calculation is correct. Now let's do the same for constructing the moment diagram. There is an initial moment on the very left end because of a concentrated moment of MA, which is negative 4,500 pound-feet. Moving to the right before getting to the distributed load, the moment diagram increases because the shear diagram is positive. The magnitude of the bending moment right before the distributed load is equal to the initial value of the moment at the left, negative 4,500 pound-feet, plus the area under the shear diagram, which is a rectangle and is shown by A1. The area of this rectangle is 2110 pounds multiplied by the length of 5 feet. Adding that to the initial moment results in 6,050 pound-feet right before getting to the distributed load. Moving further to the right, the moment diagram still increases all the way to the intersection of the shear diagram with the horizontal axis, where the shear diagram gets 0. Because the area of the shear diagram before that point is positive, the moment diagram is increasing. After that point, the area under the shear diagram will be negative, which means the moment diagram is decreasing. So the maximum moment would be at the intersection of the shear diagram and horizontal axis. Area 2 is positive, and area 3 is negative. In order to calculate the area of these two triangles, we need to identify the intersection of the shear diagram and horizontal axis, which is shown by X. X is equal to the initial value of the shear divided by slope of the line, W. After determining the position of the intersection line, we can determine the area 2 and area 3. And the moment right at the end of the distributed load is equal to the initial moment plus area 2 plus area 3. Note that area 3 is negative, so it's going to be subtracted from the previous two values. Moving further to the right side, area 4 is also negative, so we calculate the area of this rectangle and subtract it from the initial moment right after the distributed load. Moving to the right side of support at B, there is no jump on the moment diagram because there is no concentrated moment, but now the moment goes upward because the area under the shear diagram is now positive, and the increment would be linear because the shear diagram is constant. Adding all of the areas together results in a 0 moment at the very right end, which shows the calculation is correct, because at the very right end, there is no concentrated moment and there is no fixed support, so the moment at the very right end should be equal to 0, which is the case after doing the calculation. So these are some examples to show how to draw the shear and moment diagrams using graphical methods. There are some other examples that you can practice to make sure how to use these graphical methods to construct the shear and moment diagrams. Remember, the main idea of constructing the shear and moment diagrams is to identify the maximum values of shear and moments. Looking at this example, the maximum value of positive shear diagram is 2110 pounds, and the maximum value of negative shear diagram is negative 3490 pounds. Typically on the shear diagram, we look for the maximum absolute value. So the maximum absolute shear value in this diagram would be equal to 3490 pounds. On the other side, for the moment diagram, we typically need both maximum positive value and maximum negative value. Looking at the constructed moment diagram, the maximum negative value in this case is a negative 6450 pounds at support B, and the maximum positive value is 92.25 pound-feet at the intersection of the shear diagram and horizontal axis. Another takeaway from this example is that the maximum moment always happens at the intersection of the shear diagram and horizontal axis. This is very important note that allows us to quickly find the location of the maximum moments in the beams and calculate them faster. For instance, in this problem, if the goal is determining what is the maximum moment, either positive or negative, there is no need to make the entire moment diagram. We know that the maximum moment would happen at the intersection of the shear diagram and horizontal axis, so the maximum moment would be either here or here. In order to calculate the maximum positive moment, we just need to calculate area 1 and area 2. And in order to calculate the maximum negative moment, there is no need to calculate area 1, 2, 3, and 4. We can start from the right side and just calculate area 5, because the moment at the right side is equal to 0. So the moment at B would be equal to the area 5, but with opposite sign, because we have started from the right side. So in this way, the candidates for the maximum moments would be either area 1 plus area 2 as the positive moment, and area 5 as the negative moment. In addition, we also always check the beginning and the end. The moment at the beginning is negative 4,500 pounds, and the moment at the end is 0. So by looking at these moments, we can quickly identify what is the maximum positive and maximum negative moments in this problem without constructing the entire moment diagram. Alright, there are some other videos and practice problems that I will put a link down in the description below that you can watch and practice to make sure that you understand the concept of shear and moment diagrams properly. Thank you very much, and I will see you on the next lecture.